All right. Hello, everyone. Welcome to lesson 22. Today, we're going to talk about concavity and the second derivative test. So on the previous lesson, we found out what the first derivative could tell us about a function. We found out tells us where it's increasing or decreasing and where we could have local mins and maxes, among other things. Today, we're going to learn what the second derivative, or f double prime, can tell us. So to illustrate this, I'm going to draw kind of a generic function here. Something like this. And I want to take a look at the tangent lines of this function. So here, for example, we may have a tangent line like this. Here we have a tangent line. Well, maybe not quite that oriented that upwards, but I don't like that. Here we have a tangent line like this. And one thing that all of the tangent lines, at least in this region, have in common is that they're all above the curve, meaning if we extended them, those points would be of greater value than we have on the curve here. However, once we get over to this region where it dips in and we begin drawing tangent lines, we see that our tangent lines are actually going to be below the curve here. So if we extend them out, all of the values of the tangent lines will be less than the actual values on the function. All right, so whether our tangent lines are above or below, um, that property has a particular name. So this region right here where the tangent lines are above, when tangent lines are above the curve, it is concave down. So notice that the way I kind of think of it when I think of it as concave down is that it's sort of like a frowning face. So it's going like this, and all the tangent lines will be above it. And in the same way, when the tangent lines are below the curve, it is concave up. So in this region right here, we have it looking more like a smiley face. So concave up looks like this, and concave down looks like this. All right, now how can we tell without graphing whether we're going to have something be concave up or concave down? Well, it turns out that we're going to be concave down whenever our second derivative is less than 0, and we're going to be concave up whenever our second derivative is greater than 0. All right, now why would we care about this? Well, it's not so much that the tangent lines being above or below the curve, although this does have some implications if we're using tangent lines to estimate. Knowing the concavity of your curve can tell you which way it bends. So suppose, for example, we knew that f prime of x was greater than 0 for some reason. So remember, from the previous lesson, we learned that this means that our function is increasing. And so let's say we wanted to draw our function in that region. We could draw it looking like this, and that would certainly be an increasing function. But on the other hand, we could also draw it like this, and that too would be increasing. So just knowing whether a function's increasing or decreasing alone doesn't quite tell you which way it's going to bend. However, with concavity, we would see that this part of the curve, or this curve, has f double prime being negative, whereas this curve has f double prime being positive. So if we also know the sign of the second derivative, then we can tell which way the curve is going to bend. And this makes for more accurate pictures. All right, now, so we talked about if f double prime is less than 0, f double prime is greater than 0. So what happens if f double prime of x equals 0? Well, we saw what happened when we had f prime equaling 0. That was going to be a critical point. So we have something kind of similar, but not exactly the same, for f double prime called an inflection point. So what is an inflection point? And inflection point, which I'll abbreviate like this from now on, is a point x where f double prime changes sign, and we also need to be x in the domain of our function. So we do need x to be a number that we can plug into our function, just like a critical point, but an inflection point is where f double prime changes sign. Now let's compare this to the definition of the critical point, because they are a little bit different. A critical point is point in the domain of f, so that part they share in common, where f prime of x equals 0 or is undefined. Now, an inflection point can only happen when f double prime is 0 or undefined. F double prime of x needs to be 0 or undefined for it to even have a chance of being an inflection point. But a critical point, let's say we were drawing our number line like we were doing last time, a critical point can still be a critical point even if the derivative keeps the same sign before and after. So this would be an acceptable critical point. However, if we did the similar thing with f double prime and we didn't change sign right there, even if the second derivative was 0 or undefined, this would not be an inflection point. So that's one key difference between critical points and inflection points. It's a bit harder to be inflection point because you actually need to change sign of your concavity as you move over it. So there's a little bit of a subtlety there. All right, so let's take a look at an example here. So let's say that f of x is going to be x cubed. Let's see if we can find an inflection point, if it has one at all. And just like critical points, we don't need to have an inflection point. F prime is 3x squared, and f double prime is going to be 6x. All right, well, obviously this is going to be undefined anywhere, but clearly it's going to be 0 at x equals 0. So if we draw a number line here, we put 0 here. If we put in a negative value in for 6x, it's going to be negative. And if we put in a positive value for 6x, it's going to be positive. So this is an inflection point. And you can see it on the graph of x cubed. We're going to be concave down, and then we're going to be concave up afterwards. All right, now another example, or kind of like a non-example, f of x, if we have it be x to the 4th, then f prime is 4x cubed, and f double prime is 12x squared. So we see that once again, we have x equals 0 as a place where our second derivative is 0. But this time when we plot it on our number line, we have 12x squared. So whether we plug in a negative or positive number, the result will be positive, and this will not count as an inflection point. And again, if we look at the graph here, you can see that we're actually going to be concave up the whole time, maybe except at 0, where this curve sort of flattens out and isn't one way or the other. But this would not count as an inflection point. So I want to be clear about the difference. All right. So let's take a look at another example here. Let's see. Let's find where the function f of x is x squared plus 4 sine of x is concave up or down. So we need to classify those regions. And the other thing we want to do is we want to find the inflection points. We want to see where it's concave up or down and if it switches concavity anywhere along the way. All right, well, concavity and inflection points all have to do with the second derivative, so we certainly need to find that. We do f prime here. We have 2x plus 4 cosine of x. And then with f double prime, we take the derivative again, and we have 2 minus 4 sine of x. Actually, wait a minute. So this is a so this is a periodic function right here. So I'm actually going to limit this to 0 to 2 pi. How about we do that? Because then there are going to be infinitely many inflection points if we don't do that. All right, so let's see here. So we want to see where this is 0 or undefined. Now, sine isn't going to be undefined anywhere, so we just need to see where this is going to equal 0. So I'm going to add 4 sine of x over here, and I'm going to divide by 4. So this means that 1/2 will be sine of x. And in the interval 0 to 2 pi, this is going to happen when x is pi over 6 or 5 pi over 6. All right, so these are our potential inflection points here. Remember, they're not necessarily inflection points. They're only inflection points if the sign of f double prime changes as we move over them. Okay, so let's plug in something a little bit less than pi over 6. So if we do that, then sine of x will be a little bit less than 1/2, meaning that this will be positive. Then we can plug in something in between here, like maybe pi over 2. Sine will be 1, so we're certainly going to be negative for that region, for f double prime. And then after 5 pi over 6, like say we plug in pi, then we're going to end up being positive thereafter. So it looks like we're going to be concave up on the interval 0 to pi over 6. And then remember, if our intervals are disjointed, we put the union sign. And then we have 5 pi over 6 to 2 pi. So for most of this interval, we're going to be concave up, but we will be concave down in the interval from pi over 6 to 5 pi over 6. All right, and then also we notice that the sign changes over every single one of these potential inflection points. So it turns out that x equals pi over 6 and 5 pi over 6 are, in fact, inflection points. These change sign here. All right, so there we go. So there's an example where we're finding where a function's concave up or down and where we find some inflection points. And this procedure here, doing this little part right here, is going to be one step in a larger process we're going to see in lesson 24. And this will enable us to sketch graphs. And it'll tell us whether our curve is bending upwards or it's bending downwards. So it's concave up or down. All right. Let's take a look at the next problem here. So for this example, I want to sketch a graph of a function f of x where the following things are true. So f prime of x is less than 0 when x is less than -1. F prime of x is greater than 0 when x is in between -1 and 1. And f prime becomes negative again after x exceeds 1. All right. The next piece of information we're going to have is about f double prime. F double prime will be positive when x is negative, and we have the reverse situation here. F double prime will be negative when x is positive. And then finally, we only know one thing about the function itself. We know that f of 0 has got to be 1. All right, so this is all of our given information. We have these 6 pieces of information. So let's see if we can draw a graph based on this. Now, they don't tell us what the formula for the function is, and there are a lot of different functions that can have all of these properties being true. So there's really not one correct answer, but we just want our sketch to reflect this information. All right, so let's do the easiest one first. F of 0 is 1, so let's say 1 is right here, for example. All right, now we know we need to be concave up for negative numbers. So when we're on this side of the graph, we have to look like a smiley face. So when we're decreasing, we're going to be decreasing but concave up to -1. So let's put -1 here. We're decreasing, but we're bending upwards like this until we get to this point right here. All right. Then in between -1 and 1, we need to be increasing, but since we're still negative, we still need to be concave up. So maybe we look something like this. We're going to continue increasing past here, but now we're going to be concave down because everything to the right here is going to be concave down. And that continues until 1. And then finally, after 1, we're going to be decreasing because our derivative's negative, and we're still going to be concave down. So we're going to end up looking like this. So there we go. There's an example of a graph that's concave up on the left, concave down on the right, and increases and decreases according to these conditions, and goes through this point right here. And granted, I could have drawn this in many different ways. I could have had it start up here and then maybe do something like this, or I could have made this more shallow or something like that. But as long as we meet these requirements, any graph is acceptable. All right, now I want to take a look at this graph before we move on. Notice that we have a local minimum here, and this is where f prime is 0. And we have a local maximum here, also where f prime is 0. We already know these are critical points, and we could use the first derivative test that we learned last time to tell us that they're going to be local mins and maxes. But notice that this local min occurred when f double prime was positive, and this local max occurred when f double prime was negative. Now, this isn't a coincidence. This isn't just true of this particular function right here. This is actually true of any function. And this gives rise to what's called the second derivative test. Okay, so for the second derivative test, suppose x equals c is a critical point. So remember, local maxes or mins can only happen at critical points, and critical points are where the derivative is 0 or undefined, and it's in the domain of your function. All right, so if we have x being c, then there's one of two, actually one of three scenarios here. All right. If f prime of c is 0 and f double prime of c is positive, c is a local minimum. And then we have f prime of c being 0 and f double prime of c being negative, then we have the other situation. C is a local max. Okay, now if f prime of c is f double prime of c and they're both 0, the second derivative test is inconclusive. So what does this mean? It means that we need to resort to the first derivative test or some other method to tell us whether we're going to have a local min or max. And this really could go either way. So for example, if we had f of x being x to the 4th, we would see that both the derivative and the second derivative are 0 at the same place. So the second derivative test wouldn't tell us anything necessarily. But in this case, it would be, we would have a local minimum there. But on the other hand, if we had the exact same scenario, only we had negative x to the 4th, we would have a local max instead. So this kind of goes to show you that it could go either way if we have both of our derivatives being 0 here. But if f double prime is positive or negative, then we do have a concrete conclusion here. All right. So let's go ahead and take a look at some examples of this. All right. So let's use the second derivative test to find the local mins and maxes of the function f of x is x cubed minus x squared minus x plus 1. All right. So local mins and maxes can only occur at critical points. Like that was a hypothesis of this theorem right here. Oh, actually, one thing I forgot to say about this. So we suppose that f prime of c was 0 for all of these cases, but critical points can also happen where f prime is undefined. So how will that work with the second derivative test? Well, it turns out that if f prime doesn't exist, then f double prime won't exist as well. You need to be able to have a first derivative before you could even have a second derivative. So the second derivative test doesn't work for critical points where f prime is undefined. So I just wanted to lay that out there. All right. So let's find our critical points for this polynomial. And we won't have to worry about undefined points since it's a polynomial. We have 3x squared minus 2x minus 1. So this is going to be f prime here. All right, and let's find f double prime while we're at it, because we're going to need to know about concavity. So we bring 2 down, multiply by 3. So we end up getting 6x minus 2 for f double prime. All right, now our critical points will happen where f prime is 0. So let's see if we could solve this equation when it's set equal to 0. All right, so if I multiply 3 and negative 1, I need two numbers that multiply to be negative 3 and add to be negative 2. So that will be negative 3x and x. All right, let's factor by grouping here. So we end up with 3x plus 1 times x minus 1 equaling 0 for our f prime equation. All right, so this leads us to find two critical points. We have x equals 1, and if we set this part equal to 0, we'll have x equals negative 1/3. So those are our critical points. All right, now what we're going to do is we're going to plug these into the second derivative, and that will let us know whether we have a local min or max. So for example, we have f double prime of 1. That'll be 6 times 1 minus 2, which is 4. And last I checked, 4 is greater than 0. So since we have a positive second derivative and a 0 first derivative, this means that x equals 1 is a local minimum. All right, now how about negative 1/3? So if I plug in negative 1/3 into here, I have negative 2 minus 2 will be negative 4. And that'll be less than 0. So it turns out that x equals negative 1/3 will be a local maximum. Now, it's kind of odd that the lower number, or having something be negative, would give you a maximum, something positive give you a minimum. But remember what concavity is. If we have something that's concave up, like in this instance, it's going to look like a valley or a smiley face. And so the critical point in there will be at the bottom, or a minimum. And then we have the other situation here where we're concave down. Our critical point will occur at the top of the hill or at the top of our frowny face right here. So it's a little bit counterintuitive that a negative would give a max, a positive would give a min, but this is the reason why. All right. Now, so this implies with the second derivative test that we have two different ways of finding local extrema. So which one do you use? And the answer is you can use whichever one you like. My personal bias is towards using the first derivative test because it works for critical points that are undefined and it doesn't have any possibility of being inconclusive. The time I would say to use the second derivative test is if you need to find the second derivative anyway for some other reason. You're already going to have to compute the second derivative, then it's not too hard to plug the critical points into there to see if they're positive or negative. So it can be quicker if you were already going to have to compute the second derivative anyways. All right, let's go ahead and take a look at one more example here. Okay, our final example here. This is going to be the function f of x is 2x to the 5/3 minus 5x to the 2/3. All right, so what we're going to do here is we're going to find local mins and maxes, and this time we'll also find inflection points as well. We'll see if we can find any of those. All right, so, and we're going to practice, we could use the first derivative test to find those local extrema, but we're going to use the second derivative test to get practice with that. All right, so in order to do any of this, we need to find our derivatives. And thankfully, this is just going to require the power rule. So we bring down 5/3 to the front, giving us 10/3 x to the 2/3. And then we bring this 2/3 down here, giving us 10/3 x to the negative 1/3. All right, and then for f double prime, we do the same thing again. We multiply by 2/3 here, giving us 20/9 x to the negative 1/3. And then over here, this negative times the negative will yield a positive, and then we're going to have 10/9 x to the negative 4/3. All right, so now that we have that, let's go ahead and find our critical points. So remember, our critical points have to do with f prime. So critical points will occur when f prime is either going to be undefined or 0. Now we are dividing by x to the 1/3. That's what this negative power means. It's actually in the denominator. So that means that if this is 0, we'd be dividing by 0. So that immediately tells us that x equals 0 is a critical point. Don't forget to look out for the ones that will make f prime be undefined. All right. So I think that's the only one, though, because there's nothing that can make this part divide by 0. So let's set it equal to 0 and see if we can find any of those types of critical points. All right. Now, assuming that x isn't 0, I'm just going to multiply both sides by x to the 1/3. So I have 10/3, and then this times x to the 1/3 will simply be an x. And then this times x to the 1/3 will cancel out because multiplying by your negative exponent cancels it out. All right, and then finally I can multiply both sides by 3/10, add this over, and we end up getting that x equals 1 is also a critical point. And this kind of makes sense if you look at the equation. If we plug in 1 into these, 1 to any power is 1. So we have 10/3 minus 10/3 is 0. All right, so these are our two critical points here. All right, now let's try to see if we can use the second derivative test on these. Now, unfortunately, we can't use the second derivative test on x equals 0 because it also makes f double prime undefined. It actually makes it kind of even more undefined, you could say, because it's going to affect both of these terms now. So we can't use the second derivative test for x equals 0. So this is one of the disadvantages of the test that I was mentioning earlier. However, we can use the second derivative test on x equals 1. So f double prime of 1 is 20/9 plus 10/9, which will be 30/9, or 10/3. All right, and 10/3 is greater than 0, so that means that x equals 1 is going to be a local minimum. We automatically know about that critical point. All right, now in order to find out what x equals 0 is, we need to resort to doing the first derivative test. Okay. We have 0, we have 1. Let's plug in, say, a negative number in here, like say -1. I plug -1 into here, I have 10 thirds because the negative will square away. And then the cube root of -1 is -1. So this will actually be positive. So I end up getting a positive right there. All right, and then if I do something like, say, plug in 1/2 into here, it's a bit hard to kind of see what's going to happen with 1/2 on these. But if we move to this modified version, and notice that we didn't change any signs because x is positive in this instance. If I plug in x as 1/2, this will be smaller than this. So this is going to end up being negative. All right, and then finally, if I plug in something like 2, this will certainly be larger than this. In fact, 2 to the -1/3 will make this smaller. So we're going to end up with a positive here. All right, so this tells us that x equals 0 is a local max, something the second derivative test couldn't have told us. And we could also verify that the second derivative test agrees with the first in the case of x equals 1. We have minus plus, which tells us that it's a local min. So this is kind of a prime example of why I prefer the first derivative test, because in the process of being forced to do it for 0, it was very easy to do it for 1 as well. So I honestly prefer the first derivative test, but some people prefer the second derivative test. All right, now let's see if we can find some inflection points here. Now, inflection points can occur where your f double prime is undefined or 0. Now, similar to the critical points, x equals 0 will cause this to be undefined because we'll be dividing by 0 in both these instances. So this is a potential inflection point. Remember, it's easier to be a critical point because once you make the derivative be 0 or undefined, you automatically are a critical point. But with inflection points, we additionally need to make sure that the sign changes. So this is kind of an inconvenient difference in the definition. All right, now 0 is the only number that will make this be undefined. So let's set the second derivative equal to 0 to find those types of at least potential inflection points. So we have 20 over 9 x to the -1/3 plus 10/9 x to the -4/3. That will equal 0. All right, now what I'm going to do is I'm going to multiply both sides by x to the 4/3. So x to the 4/3 times this will make x to the 3/3, or x. And x to the 4/3 times x to the -4/3 will cancel out. All right, and then we can multiply both sides by 9, divide by 10, subtract this over, which will give us 2x equals -1. So x will equal -1/2 for this instance. All right, so let's go ahead and make our number line here with both of our at least potential inflection points. So -1/2 and 0, and we have f double prime. All right, so plugging in something that is less than -1/2, like say -1, for instance, this will end up being negative here, and this will be positive, but it will only be about 10/9 as opposed to 20/9 if we plug in -1 to these. So it's going to be negative here. And again, if this part doesn't quite make sense to you, you could use the simplified version, like say 2x plus 1 with this. All right. So next, when we're between -1/2 and 0, like say we were at -1/4, for instance, that will end up giving us something positive. And then if we do something like plug +1 in for these right here, it's going to end up giving us a positive number. So -1/2 did end up being an inflection point here, but 0 did not, because we don't change the sign of our concavity as we move over 0. So only -1/2 is our inflection point. All right, there we go. So we've accomplished our goal. We found the local mins and maxes and the single inflection point here. Now, again, I'll emphasize This process right here will be part of a larger process that we're going to do in order to sketch graphs in the future. So it's important that we get some practice with this now. All right, that's it for this lesson. So I will see you guys in the next lesson where we'll take a break from looking at functions and we'll learn a new way of finding the values of limits, which will end up being useful in lesson 24. So I will see you all then.